going on, everyone? Today we are going to be going over the first part of function and how this can lay the foundation for modeling and also the foundation for domain and range. Now, why exactly are linear functions important? They basically just give us a structured way to describe relationships between variables and also give us really precise analysis and also modeling. And so they serve as the building blocks for a lot of different mathematical concepts, all the way from calculus to algebra to linear algebra and other really complex topics. So these concepts are fundamental for engineering, chemistry, physics, mathematics, everything. And it could also be used in your daily life to really help you out with building spreadsheets and creating like financial forecasts and other things like that. So let's go ahead and let's take a look at what we got. So here we have a couple examples of functions. I am looking at this right here. I can already tell that this guy is going up and coming right down. And that might look like an upside down quadratic, and that's exactly what it is. So you can use a quadratic with different inputs such as time and speed and figure out how high this person is going to go, and based off the way that you model it, also how wide or how narrow. So it could really help model physical motion. It can also help us see, hey, what exactly happens with intensive care units over time? And it can also help a hospital see like, hey, if we have the weekly intensive care unit cases and there's a huge uptick in May of 2020, that, of course, would most likely be linked to COVID, but maybe there's actually a pattern here that they noticed that what if it was every May that they had this spike? And they didn't know that until they actually modeled it. And so now they have a way of saying, hey, every April or May, we should stock up on more medicine or more personal protective equipment or nursing staff and doctorate staff. So these are really important for business models, hospital models, a bunch of different type of stuff. And you can even see that if we're having an Ebola outbreak, you can also see the limitations of that, because if this exponential curve kept going up and up and up, and this kept tailing on and on and on, that's where the idea of domain and range come into play, because those restrictions that you put upon a model or put upon any kind of linear programming, that is going to help you really make the model the most accurate. So let's take a look at what we're actually talking about. So what exactly is a function? All it is just a relationship between two sets. And for our purposes, our sets are going to be inputs and outputs. So the domain is going to be the set of inputs, and then what we call the range is the set of outputs. And for most cases, and especially with what we do in the first part of this course, the domain is going to be your x and your range is going to be y. So think of your domain as anything that you put in along the x coordinate or put into the x variable in an equation. And think of the range as the y, the output, what goes up and down. So you can think of independent and dependent. You can think of input and output, or x and y. Those are all valid ways of thinking about this for right now. So let's take a look at our inputs here. And so our inputs are 3, 5, and 6. It's just a set of inputs that are inside of our domain. It's what we put into a function. And what exactly is our function right now? It's 2x minus 1, just a simple linear function. So if I'm mapping this over to the range, all I have to do is think, hey, well, if 3 needs to map over here to the range by this mapping, 2x minus 1, all you need to do is take 3 and put it in for x. So this would look like 2 times 3, because that's our x, minus 1, 6 minus 1, that's going to give us 5. I'm going to have 3 to 5. If I plug in 5 times 2 is 10, minus 1, that's going to give me 9. 6 times 2 is 12, minus 1, that's going to give me 11. And let me just draw an arrow so that way I know exactly what maps to what. So here I have mapped 3 different inputs in our domain, 3 different elements of the set, to 3 different outputs, part of our range. Now, as far as the definition is concerned, a function, which you might have already heard a lot, but maybe not have ever had a formal explanation of, is just a relation between two sets in which every element of the first set, which is the input or the independent variable, and while not always, in our circumstances for right now, it's okay to think of this as the x variable. And that's going to map to one and only one. Another way of thinking of that is the word unique. So one and only one is quite important. Element of the second set, which is going to be our output, which is going to be our dependent variable because it depends on what we put into the function. And again, for our purposes right now, you can think of this as the y coordinate, how this is going to change vertically. So a good example of this is a many to one function, okay? So let's say I had 3 and then negative 3, and let's say that mapped to the output of 9. So remember, this is my domain, this is my range, and let's keep it at that. So what many to one means is that I have many, the many responds to here. I have 3 and -3 that is mapping to 1. It's mapping to a single value of 9. And so if you think about it, how do I get 3 to 9? And how do I get -3 to 9? All I have to do is square that value. And just a really quick chart, and just a really quick graph of that, be kind of our basic parabola here. I would have 3 here, I'd have -3 here, and let's just say that's going to go up here, all the way over here, and that is going to be at 9. So what this looks like here is a parabola because I have 3 and -3 having the same exact output of 9. That's a many to one. Many inputs to one output. Now, what is a 1 to 1? That's the most, I guess you could say basic, but that's going to be an example of a linear function. So a 1 to 1, which is also a function that has an inverse, you're going to be hearing that term later. Let's say I had 4 and 6. Then let's say I had 8 and then I had 10. And let's say I had 9 and then I had 11. Well, how do I go from 4 to 6, 8 to 10, and 9 to 11? You might already think, I am adding 2. It's that simple. So my equation would just be y equals x plus 2, because this is my x, this is my y, also my domain, also my range. So I have x and y, input, output, domain, range. So if I put into the function one of these members of the domain, I am going to get out the corresponding y value part of the range. And you can see that because if I had y equals 4 plus 2, that's going to give me 6. And I can see that that's true. 4 and 6, 4 and 6. If I added 2 to 8, I have 10, 9 to 2, I'd have 11. So that's an example of 1 to 1 because each and every individual and unique part of the domain links to exactly one individual output in the range. Now, what about a 1 to many? And this is actually not a function. I'll show you why. Let's say, for instance, we had an input of 25 and we had an output, a y, of 5 and -5. Well, what would that look like on a quick graph? If I actually just graph this real quick. It's not going to be perfectly to scale. But let's say here I had 25. Let's say here I had 5 and I had -5. Remember, because those are our x coordinates and our y coordinates in this example. Well, if I had 25, 5, that would be right about there. And if I had 25, -5, I'd be around there. So you can see that this looks a little weird. And what we're going to go over in the next slide is why visually you can determine why this is not a function. But for right now, if you have a 1 to many, that is the only time in these mapping diagrams that you are going to not have a function. Big red X. It's not a function. Okay? So just by looking at a graph, it's only a function if it passes what we call the vertical line test, often abbreviated to VLT, vertical line test. What that means is you quite literally take a vertical line. I'll choose yellow. Let me put a vertical line here. And what you're going to do is drag this across the graph. And what you'll notice is that no matter where I drag this yellow line, it's going to intersect with the red curve at only one point. So right here, my intersection is right there. If I dragged it over here, my intersection would be right here. And if I dragged it all the way over here, my intersection would be right there. So you can see it's only intersecting once, and that means it passes the vertical line test. So as long as it intersects with just one spot on the graph, it is a function. Take a look at this one over here. If I slide this from left to right, you'll notice the same exact thing. It's only intersecting on this function once. So since it passes the vertical line test, it is a function. So let me go ahead and give this a check mark. That's a function. I'll give this a check mark. That's a function. And just like our last example, when we had the 25 mapping to 5 and -5, our 1 to many, you can see right here, it's kind of intersecting at 2 points. So if on this vertical line that you draw, if it intersects at more than one point, it is not a function, because what you can see is that you're going to have a 1 to many example. So if, for instance, let's say that this is, so let's just say this is 3, and let's say this is 9, and this is -9. So you can see that we have one input, the 3, mapping to two outputs, 9 and -9. So that is a one-to-many. That is not a function. It fails the vertical line test because it crosses this graph more than once, in this case twice. Now, a quick example. So let's say that we have a set of -3, -2, 0, and 2. That's the set A. These are the elements in that set. Perhaps the terminology is familiar to you. Perhaps it's not. And what we're doing is we're mapping these sets of inputs, -3, -2, 0, and 2, to a set of corresponding outputs with the mapping of 2x squared minus 1. So what that means is we're going to have a set of inputs of -3, -2, 0, and 2. And what we're going to map that to is a set, I'll put that as domain, our domain, our input, which is also set A. And we're going to map that to some outputs, this to a set of outputs in our range by the mapping of 2x squared minus 1. So what happens when I plug in -3 into 2x squared minus 1? So I'm going to do this one by hand because what's really important for you to remember is that if I'm plugging in -3, I have to remember these parentheses. That is so incredibly important, and it's one of the most overlooked steps when you start this off. And it's going to get you the problem wrong. And it's such a simple thing to overlook. But remember that when you have 2x squared, that x is the entire value. So this x is the entire value of -3. You're squaring that entire value. You're going to be squaring -2, squaring 0, squaring 2. So always remember your parentheses. That is one of the best math tips you can have at the beginning of the school year. So back to our problem. What that's going to end up being is 2 times 9 minus 1. That'll be 18 minus 1. That's going to give me 17. So what I'm going to do is I'm going to write 17. And you can either do the rest in your head or put them in your calculator. But where you're going to end up is -2 is going to map to 7. 0 is going to map to -1. And 2 is going to map to 7. So what I'm going to do now is just draw a couple arrows so that way I know exactly what's mapping to what. Just to keep this. Okay. What you might notice is that, hey, I have -3 to 17, -2 to 7, 0 to 1, and 2 to 7. Well, I have -2 and 2 mapping to the same value. So what that is going to be is I have a many to 1 function in this one because I have many inputs, in which case I have -2 and 2, mapping to 1 output, which is 7 and 7. So this is what's going to be called a many to 1 function. And actually, to simplify this, what I can do is I can actually go ahead and erase this here. You're going to see that often. And when you see that kind of crisscrossing motion in these diagrams, all that means is that you're having 2 different inputs mapping to the same output. So what is that going to look like? Well, if you actually go into your graphic display calculator and graph this, what you're going to find is that this ends up being a quadratic. What you'll notice right here is I now have 2x squared minus 1 on a graph. And if you think about a vertical line, you could even just use your pencil or maybe even your finger. And if you drag this along the curve, you're going to notice that it's only intersecting with that line that you either drew or that you used with an object. It's only going to intersect that graph once. So what does that mean? It means that this passes the vertical line test and it is a function. In this case, we have a many to 1 function taking the form of a quadratic, and it's passing the vertical line test because it's only intersecting with the graph once. All right, so I hope we laid the foundation on what these diagrams look like, why these arrows go to the places that they go, and what some of these functions or non-functions look like graphically, but also in a diagram. In this video, we're going to take a deeper dive into domain and range and what exactly those look like as well, graphically and numerically. I'll see you in the next one.